Hi friends, this is Eric White. Today I'm going to discuss building super high performance Open XML document processing applications. This screencast is going to focus on a high level of this technique, and I'm going to demonstrate the code. In the next screencast, I'm going to walk through the code in detail so it will be easy for you to take this code and alter it for your particular scenario. If you've ever built an OpenXML application that processes hundreds or thousands or even tens of thousands of documents, and if you have made this be just a single threaded application, then you'll notice that you're only using about 25% of the CPU on a 4-core machine. Well, it follows from there that if you make a multi-threaded application, you'll get a whole lot better performance. And in fact, you do. However, there's a problem. If you build a multi-threaded application, and if you are processing documents of any size, in other words, documents that are occasionally 5 megabytes or 10 megabytes in size, then periodically you'll see some exceptions that are thrown from deep within system.io.packaging. These are the object disposed exception, and if you code in a slightly different fashion, you'll see null reference exceptions. What's bad about these types of errors is they don't seem to be repeatable. You'll make a very nice OpenXML application, you will test it out, it runs just fine there on your developer machine, and then you deploy it in the real world, and then periodically you'll see these object disposed exceptions. Well, the question is, why do we see these types of exceptions? The Open XML SDK uses system.io.packaging, which underneath uses isolated storage. And the problem occurs whenever system.io.packaging uses above a certain threshold, which is approximately 10 megabytes, then system.io.packaging starts storing content in isolated storage rather than just in memory. Isolated storage uses a secret directory. This name of this secret directory is unique to the strong name of the assembly that is using system.io.packaging. In other words, it's also unique to the strong name of the assembly or of the exe that is using the Open XML SDK. If you make a multi-threaded application, then both of these threads are going to be using this same secret directory in isolated storage. And what happens is that this then causes a conflict. Further, even if you take a particular executable and run it multiple times on the same machine, then executable 1 starts, it puts contents in this secret directory. Executable 2 does it also. Executable 1 finishes and clears out or modifies that secret directory, not taking into consideration that there's another user of that directory, and then executable 2 either throws an object disposed exception or it throws a null reference exception. But the problem is this doesn't happen all the time. It only happens when your usage of documents is such that you're going to use above 10 megabytes of storage. There is an approach that we can take to mitigate this. The summary of the approach is that we're going to put all of this code to modify Open XML documents into its own program. By the way, when I talk about docx modification, the exact same issues apply to XLSX modification or PPTX modification. For our 4-process machine, we're going to create 4 separate executables, and we're going to tweak each executable so that each has their own strong name. We're going to write a controller program that operates on a different machine that uses MSMQ to communicate to these daemons that run on the document modification machine. And finally, we're going to also use a RAM disk. This will also help us to gain really good performance. This approach is very similar to the approach that I showed in the screencast on building ultra high performance document generation applications. We're going to have these 4 daemons that execute. The controller is going to sit over here on a different machine. The first thing that the controller does is it sends a ping message to the daemon just to see if it's alive. And the daemon turns around and sends a ready message back to the controller. The controller then sends a request to the daemon to process some documents. And the daemon, after it's done processing that set of documents, sends a message back to the controller telling it that the document process is complete. It then sends back some XML that contains a report of how that processing went. If the processing of those documents resulted in thrown exceptions, we want to know about that. If those documents happen to be invalid documents and the Open XML SDK wouldn't open them, we want to know about that. And further, we want to know whether that process hung or took too long. After the document process complete message is sent back to the controller knows that that particular daemon is now free, and it sends a new request to process some additional documents. This approach is very similar to the approach that I showed with high performance OpenXML document generation. However, there are a few wrinkles in this approach. First of all, we are processing some arbitrary set of documents. In my experience, it's harder to write code that always operates correctly on arbitrary documents, including documents that might be invalid, than it is to write reliable code that generates documents. When you are writing code to generate documents, you're working with a known data set and you're generating some specific documents probably according to a template. You have control over that template and you know that that template is valid. When you are writing code to operate on an existing set of documents, those documents might be valid and they might not. So if the Open XML SDK or something else throws an exception in that document processing, we want to know about it back in the control program. So when the daemon sees some of these exceptions, we need to send that information back in the payload of the message that goes back to the controller program. Another thing that I think is important when writing this type of code is to be prepared for a situation where the code doesn't terminate properly. Maybe it starts running forever. There's nothing more annoying when you're trying to debug an OpenXML program than having your daemon out there just hang, and then you have to stop the daemon, start the run over again, figure out what the document is that didn't complete, and so on. So we want to take an approach where if processing goes beyond a certain threshold, we want to stop processing and note that fact in the message that's passed back to the controller program. The daemon takes care of all such issues. As with the high-performance document generation example that I presented, the way that we're going to create these daemons is we'll create, first of all, a prototype daemon, and then we will run a PowerShell script that copies that prototype daemon to a new source file and then goes in and makes appropriate modifications to that source file so that when we compile that modified source file, we get an executable that has its own strong name that is completely separate from the other executables and their strong names. Let's take a look at the build and run daemons.ps1 script. Up at the top here we can set the number of daemons. If you have an 8-core machine or more, you very well may want to bump this number of daemons to higher than 4. I've actually seen where if you put this to 5, you get a very small amount of performance gain over 4, but it's almost negligible. And then the problem with that is it makes the machine less responsive if you need to go do something on that machine. So here's what the code does. It gets that high performance docx modification daemon.cs file and replaces the string static int daemon number equal 1 with the string static int daemon number equals $i. Further, it takes the properties/assembly info.cs file and it goes into that file and it changes the name of the executable from high perf docx modification daemon to that same name with the daemon number appended to the name. And further, it changes the version number from 1.0.0.0 to 1.0.0. and the daemon number. These two modifications ensure that we are going to have a completely separate strong name for this daemon executable. And what that means is isolated storage will give a separate directory to each one of these daemons, and we will never get into this conflict where two separate executables or two separate threads are accessing that isolated storage directory incorrectly. The next thing that this PowerShell script does is it compiles that C# file, it puts it together with the assembly info file that we created. This particular example accepts revisions in all of the documents in a given directory. So I've included 4 PowerShell C# files in there. And then finally I've included the various references to other assemblies that we need in order to correctly compile this program. And last but not least, the PowerShell script iterates through each one of those daemons and starts it up with a window style of normal. And in this way, we can see those daemons in operation. So let's run that PowerShell script. There it goes. It compiles those 4 daemons and starts them up. They are now ready to do our bidding. I have 2 directories here. I have a directory source document, and if we go into this directory, we see that I have 8,002 docx files. And if I go into this processed documents directory, there's nothing in it at this moment. Now let's go look a little bit at this controller program. Up at the top of this class, it's initialized a few variables, such as the machine name of the machine where all the daemons are going to run. Again, we have the number of daemons here set to 4. Of course, when you build your own system to do processing such as this, you'll probably want to push out these parameters maybe into a database that both machines can access or something. You'll want to make it so that it isn't just hard-coded in each of the 2 machines. Another thing that we have here is we have the timeout in seconds. I'll change this timeout in seconds here to 5 seconds. So this says that if accepting revisions in any document in that document list takes more than 5 seconds, we're going to stop it and report that that process timed out for that particular document. We also have the names of the various queues. The name of the queue on the controller machine is the process documents controller. That's its queue name. The way MSM queue works is that you need to refer to a queue differently when you're on the machine where the queue is located and when you are on a different machine from where the queue is located. So here this is putting together the remote name of the queue that we're going to pass to each one of those daemons. It's this string right here, and that's how those daemons are going to know to send the message back to the correct queue. Another thing that we do here is we initialize the name of all of the process documents queues. These are the queues that are in each one of those daemons. We initialize those as appropriate, and then we set these directories as appropriate. These are the directories that contain the source documents and the processed documents after we're all done. So let's run this here. Over here we can see our daemons already, and here we can press F5, and sure enough we can see these daemons are over here happily processing documents, accepting revisions in each one of those documents. And over here in this machine, this is the machine that is controlling those daemons. It's noting when those daemons have finished processing a set of documents, and it's tracking how many documents per minute that we are processing. So this is going to vary widely based on what your code does over there. If you have code that executes some processing and time-intensive operations, you'll get a lot fewer documents per minute than if you have something that is very simple. And it's all finished. In the end, we are getting 6,992 documents per minute. Here we have the run report that was generated by that process. Let's look at it in an editor. We can see that for a vast majority of these documents, they process just fine. If there's nothing other than just the name of the document, that means that processing was successful. But here we have an exception that was thrown because the archive file cannot be size 0. The Open XML SDK will not load up a file that doesn't have any content in it. Here's a case where system.io.fileFormat exception was thrown because the file contains corrupted data. If I look for timeout, then I can find this particular document, 2787.docx, timed out after 5 seconds. If I believe that my code should be processing faster than that, then I can certainly go look at that document and run my code on just that document and find out why the processing is taking so long. That's all I'm going to cover in this screencast. That's enough. In the next screencast, I'm going to walk through the code in detail so that you can more easily alter the code for your particular scenario. See you in that screencast.